Yeah, you are.
Good stuff. See you all. Let's get your cameras on. Ready to go again. Good, all happy, all smiley. Good. Yeah, but the problem with the links up there, guys, they didn't send me the link for the Teams, so I couldn't get on for a while. You've not missed much, don't worry. I'll just sing them back.
Max.
There we go. All right, let's see. Hopefully I've got everything working now. So did you have your Module 17 exam on Sunday?
Yeah.
How did it go? Confident? Happy? Or was it hard? Or was it easy? It was postponed. Oh, okay, okay. I was wondering because I'm not out there. So exam's been postponed. Oh well, that gives you more time to revise, if that helps. When have they postponed it until? Anybody? Have you got a new date for Module 17? Hello? Anybody? Number 16. You've got your camera on. Have you got a new date for Module 17?
Not yet.
Not yet. Okay. No worries. No worries. Okay, guys. Right. Well, we're back on again, thankfully, eventually. The links eventually worked. Okay, so we've got 2 weeks now of Module 15, gas turbines. This is what I call my bread and butter. This is what I joined the Air Force to do, work on aircraft, jet engines. Even as a cadet, you know, jet engines are sort of my bread and butter, as they call it. So hopefully we'll get through this. We've got 4 books. Hopefully you've got all 4 books out there. It's been in PDF or hard soft copies, whichever version you've got. Okay, so has everybody got the 4 books? Just make sure you've got all 4 books. Yeah? Okay, good.
Yeah.
Good, good, good. Oh, sorry, Sanjeev, just 2 seconds, just get a phone call from Sanjeev.
Interview नहीं देना पाएगा।
Harry, ओ Harry,
हजुर दाइ
के भयो म्युट भएर खाने उसको आवाज?
खोइ थाहा छैन
फोनमा बोल्दै छ।
कति पेज नम्बरमा हो साथी हो?
पेज नम्बर सुरु भएको छैन त के पेज नम्बर भन्नुहुन्छ
हो कुन बुक पाठगार हो?
बुक 1
ए ल बुक 1 ल। त्यही भने म त भर्खर खोल्दै छु के।
पेज नम्बर 5 पुगिसक्यो त।
5 पुगिसक्यो?
अँ।
सौरभ ल 5
Chat to Sanjeev there. I'll just go and message. Quick message now before I forget. Okay, 2 seconds. Don't worry, I've got plenty of time for the sorry, so I'm sending a quick message now. Okay, right. So yeah, 2 weeks, 4 books, and you will have 92 questions of fun eventually whenever you get exam. Prabin, nice to see you. Man the camera.
Serious? Yeah.
Okay, so yeah, let's get this ball started. What time is it now? 25 to 10 already. My goodness, it's time. Well, 25 to 10 my time. It's afternoon for you guys. And we've had snow so far. We've not in my town, but set in the high hills. We've had snow. It's been cold. It's been storms. We've had lots of stuff. Hope it's nice and warm out there for you guys. Okay, right. Let's move on. Let's get this module 15 working. So yeah, just usual. It's me again. So you got me for 15. Again, if you want any questions, there's my work email on the bottom. Okay, so if you have any questions as we go through the course, I will certainly check them and try and answer them as best as I can. Okay, so today we're going to start in book 1. We'll do book 1, book 2, and a little bit of book 3 towards the end of maybe Friday, possibly, because I'll try and keep next Friday. A week on Friday will be the last day. And we'll try and keep that day for revision. Okay, just like we did with module 17. There are questions in every book. You've got books 1, 2, 3, and 4. You might have had a look through already. There are questions in the book for self-revision, and I will help you with those as well. I've got lots and lots of questions for revision towards the end of the course. We'll have a bit of fun, little pop quiz and that sort of thing. And so don't worry, there's lots of revision. And if I want to give you some stuff to hand out, I will do as well, as you see fit. Okay. As usual, just like we did module 17, if you have any feedback on the course, okay, just make sure you go online and you can put some course feedback in there as well. Anything you don't agree with the book, even myself, whatever you think we can improve. Oh, don't want that. What's happened there? Get back. Oh, my PowerPoint has crashed. Fantastic. Just what I want to do. Bear with me. Okay. 2 seconds, guys. My PowerPoint's crashed. Just what I don't want. We'll try again. Computer's been funny again. Part 1, let's go. Why it's done that, I have no idea. There we go, back again. Right, let's see if we can get any problems, please put feedback on the course at all. Exam breakdowns, as I said, you will have 92 questions of fun at some point. Okay. We're looking at fundamentals, engine performance, inlet. Let's change my pen again. Compressors, combustion section, turbine section, exhaust, thrust reverse, bearings, lubricants, lubrication systems, fuel systems, FADEC, air systems, starting ignition systems, engine indication, power augmentation, turboprop, turboshaft engines, APUs, power plants, fire protection systems, engine monitoring, and finally engine stores and preservation. Lots of topics, okay, and you see there 92 questions. All right, and you'll see the levels are pretty much all level 2 except level 1, which is nice and easy, power augmentation in there, and we do have a level 3 on engine monitoring and ground operation. Okay, so that's one of the slightly harder ones, so keep a note of those sections. Now the questions do vary from 5s, 4s and 3s. We do have indication about 6, but again, remember, this is just a guide because the questions can change by approximately 25%. So I'm just putting that as a rough guide to let you see what's going on. Okay, so there's good even split. Engine monitoring, we've got roughly 6 questions there. I say power plant, 6 questions, a lot heavy there, but the rest are all 3s and 4s thereabout, and generally most of them are level 2. There's a nice easy one, power augmentation, and a slightly harder one in the engine monitoring and ground operation, which will be in book 4. Okay, so it gives a little breakdown of the potential of the questions you will get. But unfortunately, you will have 92 questions. You get 1 hour and 55 for the exam. So quite a long exam. Again, all multiple choice as normal, A, B, or C. Okay, so you got a little breakdown there. So we'll start on with fundamentals. Part 1, okay, so we'll just crack on with that at the moment. I'll just move this down out the way, get these out the way. Okay, that's there, and back to you guys. Okay, so fundamentals, we're going to start with some basic back to physics. Module 17, we covered a little bits here and there as well. We're going back away. Normally we do module 15 first, and then we do module 17. But say we did module 17 first. It was only a 4-day course, just as a trial to make sure we can get the teams and that working as well. So some of it you will have covered already in 17, so hopefully it'll make it easier for 15. Look at a bit of background history and piston engine versus a gas turbine engine as well. Now somebody might fancy going into the piston engine, and if you want to do that, you can do module 16 as well, if you fancy doing that. Look at gas turbine fundamentals and major components. Get classification of propulsion units, the different types of jet engines. How the gas flows through a jet engine. And what's called engine notations as well, the numbering of certain parts of relative to the engine. Okay, so that's sort of the initial parts of fundamentals. Major components, well, we'll look at intakes, engine ice protection systems, compressor fan blades, stall and surge, airflow control, combustion systems, turbines, exhaust system, and thrust reverse as well. So quite a lot to get through. Engine noise reduction as well. Yeah, we've got a big engine on these aircraft, and it does get a bit noisy. How can we prevent that? Again, gas turbine definitions, abbreviations. We start speaking in abbreviations and terminology, so we'll look at different ones there. So at the end of all this, you should have an understanding of each chapter or book and able to take a face test at the end of the book. A face test would happen back here in Scotland with the ab initio courses. For you guys, there's no face test. You just have the big test at the end of the course. Okay. So we're going to move on and start off the good old physics. You thought you got rid of module 2, which is physics, but we do recap a little bit because now the physics part will hopefully start to make a bit more sense, relevance to gas airflow as it goes through the aircraft engine, okay, and what happens to it. But just basic, don't worry, we're not going as deep as what we did in module 2. Okay, so if you haven't done module 2, hopefully you have. If you haven't done module 2, this will be brand new to you. It's nice and straightforward, hopefully. So first one is mass. Now mass, everything in this world has a mass. The weight will change at different points around the world, and especially in space and the moon, but everything is made of mass. So neutrons, protons, electrons, etc., all the good stuff, all the good atoms. So mass is the force required to overcome the inertia or the movement of a body, and that can be classed as weight when it is associated with gravity. Okay, weight equals mass over gravity. Again, these are just terminologies. They might ask you a question, possibly, some of these terminologies, but we will recap these every day anyway. But it's more, this is more of a recap from module 2, but it's to understand when it comes to mass airflow and how airflow goes through a jet engine. Acceleration, Newton's second law. Okay, the rate of change in the velocity of a body, as velocity is the time taken for a body to travel at a given distance, then acceleration is the time taken to change that velocity. And we'll look at Newton's second law there. How will that affect us in jet engines? Well, the gas flow going through an engine, where it comes in the front and when it leaves the back end. Momentum, well, that's movement. And this is the measure of the quantity or how much of motion, and is defined as the product of the mass and the velocity of a body to bring it to rest. Yeah, we need power in an engine. So power is the rate of change in energy from one form to another of the rate of doing work. And a quick example is we put fuel in the aircraft and we change that fuel, which is a chemical energy, we burn it, make some sort of power. So that's a typical example. We'll cover that as we go through. And the formula for that one, your first formula, what you might to remember, is power equals energy over time. And the standard international units, or SI units, is power is measured in watts, or good old joules per second. Anything to do with energy is joules, but certainly power in this case is watts. Okay, but power, watts, or joules per second. So going back to module 2, good old gas laws. Well, Boyle's law. Does anybody remember what Boyle's law was? It was a constant what? Was it constant volume, or was it constant pressure, or was it constant temperature? Anybody?
Temperature is constant.
Yeah, good. Boyle's law, I think of Boyle's law as in boiling. So if you're boiling something, that's heat. So that's how I remember that Boyle's law is constant temperature. Yeah. So just to recap, same one from did in physics. So we've got constant temperature indicated here by a little heat source, and the gauge on the right here is reading just a certain gauge. Okay, constant temperature. So this time with constant temperature, as volume decreases, pressure increases. Okay. So pressure increases, volume decreases. In other words, we squeeze something together. We're going to compact all that, whatever it is at the time. Could be gas, could be anything. If we squeeze something, we can press that mass. Well, what's going to happen? Okay, the volume's going to decrease. All right, that's at constant temperature. In other words, the volume of a given mass whose temperature is maintained constant is inversely proportional to the gas temperature. In other words, gas pressure. Whatever happens to pressure, we'll do the opposite for volume. So if we squeeze something, we increase the pressure, we decrease the volume. So one part does the opposite. And we'll show this in the gas equation shortly. Okay, so inversely proportional. If volume goes up, pressure goes down. If volume goes down, pressure goes up. They do the opposite from each other. Okay, represented by increasing weights here, increasing, decreasing volume, decreasing, increasing volume, and so on. Okay, so that's good old Boyle's law, constant temperature. Charles' law, what's Charles' law? Constant
pressure.
Constant pressure. And this is the one that applies to jet engines. Okay, jet engines tend to work on what's called the constant pressure cycle, called the Brayton cycle. We'll cover that shortly. But just to give you a background, again, same sort of diagram, but this time we've got a constant pressure indicated here on the gauge on the left-hand side. But we're going to increase heat or decrease heat. Now this time it's directly proportional. So the constant pressure is represented by the two weights here. So the weight isn't changing, but the pressure will. So if we heat a gas, in this case, the volume is going to go up. Yeah. In the case of a jet engine, that's what we do. We get air coming in the front of the engine, we heat it by adding fuel, and it goes out the back nice and hot, so the volume expands. Yeah. Indicated in the graph here. So temperature goes up, volume goes up. So in other words, if the pressure of a given mass of a gas is maintained constant, the volume of a gas increases and its temperature is increased. In other words, directly proportional. Volume will increase and so will temperature increase. Okay, if we heat something up. Now, this is all taken from the ideal gas law. Does anybody remember what that one is? Anybody? Who can say it off without looking at the book? Anybody remember what the universal gas law? Something stated as the ideal gas law or the universal gas law or the general gas equation. There's a few different names. You can use it in hydraulics, pneumatics, fuel, lots of things. Anybody remember?
Pressure into volume equal to NRT.
Oh, there's that as well. Yeah, that's the other one. Yeah, but the general gas equation. Give you a clue. P1.
P1 V1 upon T1 is equals to P2 B2.
That's great. Thank you very much. Yeah, P1 V1 over T1 equals P2 V2 over T2. Okay. In other words, pressure, volume, and temperature of the initial one equals something in, something out. Yeah, but the something out part in this case here is that, and certainly gas turbine engine. This could be the incoming part of the engine. And that could be the outgoing part. Something's got to change. Yeah, so we'll have some sort of relationship here, and we'll have some sort of relationship here at the final product. But what goes in must come out, but it might change within that part. So let's look at different versions of it. So we looked at Boyle's law first. So taken from the general gas equation, we had Boyle's law was a constant temperature. Well, in this formula, anything that's constant we can get rid of. Yeah, so if it's constant temperature, we can get rid of the T1 and we can get rid of the T2 because they're both constant. All right, so that leaves us P1 V1 equals P2 V2. In other words, if pressure goes up, volume goes down. Yeah, inversely proportional. So if you get stuck in an exam, do P1 V1 over T1 equals P2 V2 over T2, and then whatever's constant, put your hand over the constant. What you're left with, that is the formula. Now remember, if it's in line like that, that means it is inversely proportional. In other words, this will do the different from this one. Okay, irrespective of what numbers you get put in there, just remember that this will do act different from this one. It will do the opposite. All right, what we call inversely proportional. An example is there, Boyle's law with constant temperature. Inversely proportional. Carr's law, well, that's constant pressure. So again, using your gas equation, if it's constant pressure, well, we can get rid of the P here, and we can get rid of the P this side because they are constants. Anything's a constant, we can take out of the equation. That leaves us V1 over T1 equals V2 over T2. So this time we've got V over T. Well, it looks like a fraction, so that means it's directly proportional. In other words, if volume goes up, so does temperature. Okay. And this is where we look at in a gas turbine engine. Temperature is going to increase, so volume is going to increase. In other words, when we heat that gas in the fuel mixture in the gas turbine engine, it's going to expand and go out the back of the exhaust. And this is typical for a gas turbine engine. Okay, so that formula there is directly proportional. In other words, volume and temperature will both increase or decrease accordingly. Okay, everybody happy with that so far? Just a little bit of recap from physics. Now, we said about adding heat energy at a constant volume. Now, a constant volume process is more, we'll go back into a basic engine, like a car engine or a motorbike engine, etc. Now, cars and motorbike engines, or any sort of piston engine that effect, even light aircraft, they work on what's called a constant volume process. Gas turbines work on a constant pressure process. Piston engines work on a constant volume. And we say constant volume because when the piston and engine is going up and down, when it gets to the top of the stroke, there's a space there. When it gets down to the bottom of the stroke, there's no space there. And that volume is pretty much the same. Yes, we add fuel, we add heat and expands, but we class a piston engine as a constant volume process. Okay, but we're going to look at the same for a gas turbine engine. We're going to add heat energy by igniting the fuel in the air mixture, so we're going to add heat to it, but we don't contain it. We allow all that gas to go out the back of the exhaust. But we're not containing it. But a piston engine is different. We contain that mixture, contain that heat to move that piston. We don't have pistons in gas turbine engines. We just allow the gas to go out the back end. Okay. We'll mention a basic four-stroke cycle in relation to jet engine. Okay, so I said with jet engine, we have a constant pressure. And the reason we have a constant pressure is if you look at the four-stroke cycle, is everybody happy with the four-stroke cycle? I'll go through it quickly anyway, just in case you don't know. In a four-stroke cycle, if you look at the bottom here, we have the piston goes up and down. Yeah. Now, on the intake cycle, the piston goes down and draws air in. It sucks some air in. Then we compress it. The piston comes back up. We compress that air. At the same time, there'll be fuel in there as well. As we compress it, we add a spark. You get combustion or power cycle. That goes bang. Yeah. That pushes the piston back down and gives the power stroke. And eventually, the piston comes back up and expels the gas out to exhaust. And then it starts all over again. Hence the four-stroke cycle. You get one power push for every 4 strokes of one cycle. Okay, so 4 strokes in one cycle. So you've got 1, 2, 3, 4. And the third one here is when you get the actual power. Now that's classed as what's called an intermittent cycle. We only get a bang for every 3 strokes. So you get the bam, 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 bam. Hence the noise from your piston engine. On a gas turbine engine, it does something similar, but with no pistons. We have air coming in, yeah, same as the intake cycle, the induction cycle. But this time, we do compress it, just like the compression cycle. Okay, and yes, the same with the power cycle, the combustion cycle, we do ignite it, we spark it up, we ignite the fuel and air mixture, but there's no pistons in here. We just allow it to go out the back of the exhaust. We don't keep it contained in the the cylinder. Remember, in a 4-stroke cycle, you've got inlet valves and exhaust valves. On the power cycle here, the inlet valve and the exhaust valve are closed. In other words, there's no space for exhaust gas to go. The only way it can go is to push the piston down, which will rotate your crankshaft, which will rotate your sprocket or your gearbox, which will rotate your car, your chain, etc. On a jet engine, we don't have that. We just have the expansion of the gas once it's heated up, so the volume increases, okay, so it expands out the back of the exhaust. And all we have instead of pistons, we'll have the expansion part here, we've got turbines, which will then turn the compressor, suck more air in, more fuel, and so on, and that will repeat the cycle. The principle's pretty much the same. On a 4-stroke piston engine, intermittent, we get the bang, 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 where we call it the suck, squeeze, bang, blow. That's a sort of short abbreviation for it. But on the jet engine, it's more suck, squeeze, burn, blow. We don't have a bang as such. We have a constant flame going. Whereas on a 4-stroke engine, we have an intermittent bang going on. Okay, it's only once it goes bang. Where in a jet engine, it's constantly alight. We just add or decrease fuel as we see fit. Okay, but roughly the principle is the same. Okay. Any questions on that, guys? Everybody happy between a 4-stroke cycle?
Yeah,
Question.
it's clear.
Yeah, all good. Again, it's just showing the principle. Yes, it's similar to a piston engine, where a piston engine is constant volume, but a gas turbine is a constant pressure. Now, as we go through the course, you'll see we don't always have a constant pressure, but we do regard it as a constant pressure cycle. Okay, so just keep that in mind for a moment. So let's look at energy. Types of energy we're going to use. Well, we've got heat. We need some sort of heat to provide some energy. The engine gets very hot. We need to add fuel to get the heat. Potential energy. Well, I've got the cold air coming in. That's got potential. Remember, potential is if I hold this pen up, that's potential. As soon as I let it go, that turns into kinetic. Yeah. Kinetic being the movement, in this case, of the gas flow going through the engine once it's gone on fire. Electrical, yeah, we need some spark in there. Okay, but we'll speak about that later in the books, where it can be quite lethal. So never muck about with electrical energy. It tends to make you do the funky chicken dance. And pressure energy, exactly the same energy you'll have on your exam day. Pressure, okay. We need the constant pressure in a jet engine to maintain that flow of gas from the combustion chamber through to the turbines. So we're looking at different types of energies, all right? So lots of different types, all combined together to give us the power in the engine to provide the thrust, etc. With that in mind, look at what's called a thermodynamic. Thermo, heat, dynamic, movement, engine, okay? And this heat thermodynamic is a very basic representation of what happens when we put energy into an engine and what comes out. So you've got heat energy coming in. They're represented by the Q here. So this represents the heat engine. Engine absorbs Q heat. In other words, this part here is by QH from the hot reservoir. In other words, combustion section. The engine will use some of that energy. Now, every engine is never 100% efficient. Unfortunately, we lose a little bit. But the engine will produce W, in this case is the work. Okay, this will provide the thrust. But we do lose a little bit of energy, expel some energy. So we put some in, we make use of it, engine will do some work, but unfortunately we lose a little bit as well. This is just a very basic representation of energy. Now we represent the energy by Q in this case, hot and cold. So QH, QC, hot energy, cold energy. Because when we've done the heat always goes to cold, okay? And eventually some of it is classed as wastage. But in between there, we do get a little bit of work, yeah? And the more efficient an engine is, the more work it will produce. In other words, the more thrust we can get to move your aircraft across, okay? So it's just a very basic setup for what's called a thermodynamic engine. We're going to look at this far more in depth. That's just a basic representation. Okay. Temperature scales. Again, going back to module 2. Well, I've done this already, but again, we'll just conversions. You might have to convert possibly. Now, for basic calculation, for every 1 degree, that represents 1.8 degrees Fahrenheit. So we multiply that up. But just for good old conversions, if you want to convert Fahrenheit to Celsius, centigrade, that would be it there. Okay, we do 5/9. Whatever the Fahrenheit figure is, minus 32, and then multiply by 5/9. And remember, for quick guesstimates, 5/9 is almost what? What's 5/9 almost? What's 5/9 very close to? Parabing, I'm going to pick on you because you've got your camera on. Half, yeah. So let's give an example. Let's say the Fahrenheit figure was, make it nice and easy, let's make it 64. Yeah. So we've got a Fahrenheit figure of 64. Well, 64 minus 32 is 32. Well, 5/9 is almost a half. Well, half of 32 is 16. So as a guesstimate, 64 degrees Fahrenheit is almost 16 degrees Celsius. Yeah? Does that make sense for that one? Just as a guesstimate, it's almost 5/9. If we want to go to Kelvin, we get the centigrade figure, and then we add 273. So if we converted the 64 degrees Fahrenheit to 16 degrees Celsius, well, we just add 273, and that will give us a Kelvin figure. Okay. The opposite way, if we want to convert Celsius to Fahrenheit, we multiply by 9/5 and add 32. Well, 9/5, what is 9/5 almost? What's 9/5 almost, anybody?
4.
It's almost 2, isn't it? 9/5 is almost 2. So as a guesstimate, if we had Celsius of, let's call it 10, nice easy number. Well, 9/5 is almost 2. Well, 2 times 10 is 20, plus 32 would give us an answer of roughly 52 degrees Fahrenheit as a guesstimate, because it's very close to 2. All I have to watch here is the bigger the number, if using the guesstimate, then the bigger the error. Okay, don't worry about these ones. You can have a practice. It's only if you ever have to convert. If you're maybe doing a calculation for maybe some sort of calculation in engines, more in an engine bay or something like that, then yes, you might have to do that. Okay. Over here we've got Rankine, which is Fahrenheit plus 460 degrees. Again, these Kelvin and Rankine figures are for more than we did back in physics. These are just a bit of a recap for you. Fahrenheit, Kelvin, and Rankine. Okay. Again, we'll have covered this, or you guys will have covered this certainly in Module 2. Anybody not done Module 2? Have you all done physics? Yeah. Hopefully you've all done Module 2. Yeah. Okay. So that's just a recap of how to convert from Fahrenheit to Celsius or Celsius to Fahrenheit. There's a couple of different ways of doing it as well, but just a bit of recap there, okay? Nothing too drastic, hopefully. If you can't sleep at night, you get bored, put a number in there, you can convert it in the proper way, all right? Right, Newton's laws of motions. We're going to look at 1, 2, and 3. Okay, so first law, we've got a ball here. Ball sat on the table with no outside forces. The object won't move. Yeah, we leave something on the table, as long as it's flat, that ball will stay still. If it's already rolling and there's no any external forces applied to it, it won't stop. Well, we're going to have friction, you know, that it will eventually stop. But if there's no friction, there's no applied forces, then if that ball is rolling already and nothing acts upon it, it will never stop. So we call that Newton's first law. In other words, no it will stay at rest unless acted upon. That's my old way, remember. Law, the more force, the more acceleration. So we start to get into the gas turbine thing where could relate that to? Well, we add more fuel, means more force, means we can move the engine forward, yeah? So the ball, which is now moving, if we then push it again, gives it more acceleration. That would be Newton's second law. In our case, jet engines say, add more fuel and more power. And then the one that definitely applies to a gas turbine engine is Newton's third law. Every action has an equal and opposite reaction. In other words, what goes in must come out. So the air coming in goes out, and with that air going out the exhaust of the engine, pushes the engine forward. and that engine is attached to aircraft, which pushes your aircraft forward. Equal, opposite reaction. Thrust coming out the back of the exhaust, propelling the engine forward. Equal and opposite reaction, and that's when it applies most generally to the gas turbine engine. Yes, a bit of second law involved because we add more fuel, more power, etc. So certainly 2 and 3. And you could argue Newton's first law, well, an aircraft will stay still until we get some power. Yeah. Then we move into Newton's second and third law. So they all apply, but certainly the Newton's third law when an engine is running and providing thrust definitely applies. Okay. Right, Goodall-Benou's theorem. All right, now I've got a representation here, again, recapping physics. We've got some gauges at the front here. We've got a restriction in the middle, again showing pressure differentials, and again, opens up back to the same damping here. Now what we're saying is, we're looking at the mass of air coming to this tube will have to be the same as it goes out. It might change a little bit in here, but in an ideal world, what goes in must come out. In other words, the mass goes in, must come out. We can change it by adding heat energy, shapes of the tube and that sort of thing, restrictions and whatever else. But remember, Goodall-Benou's theorem states what goes in must come out. So in this case, we've got velocity and pressure, velocity and pressure, velocity and pressure. So as you can see here, this diameter is the same as that diameter. So the speed of the gas coming in here must be the same as the speed of the gas coming out. At the moment, we've not added fuel, we've not added ignition. All we've done is made a restriction. We have a different shape here and a different shape here, where in this case, the velocity has increased, but the pressure has decreased around this smaller area. And then it opens out again, where the velocity increases, decreases again, and the pressure stabilizes again as well. Okay, why is it doing this? Well, we've got convergent duct this side, and we've got a divergent duct this side. Okay, so let's recap on both of those. Convergent duct. So there's it coming in. Okay, we've got a large area at the front and a small area towards the exiting point. Now, as the air comes in, to get through this small point, that whole mass, it's got to do two things. At least two things. The velocity has got to get faster because it can't all get through one go. If you try and put all that mass at the same speed, it will just go, it will just lock. So to ensure it goes through, it speeds up. And as it speeds up, then two things do the same thing. Pressure and temperature will decrease. Because if they didn't decrease, then, as I said, everything just stop. All right? So something has to give. So we can go faster, that's great. But remember, pressure and temperature do the opposite, they both decrease. So whatever velocity is doing, pressure and temperature must do the opposite. Okay? So in this case, again, convergent, we're coming to a point. So the velocity increases, pressure and temperature decrease. Where could that fit in an engine? The exhaust. And we'll show this in a minute. So that's, remember, a convergent duct. Velocity increase, pressure, temperature, both decrease. Then we go to the opposite end, divergent duct. So we've sped air up. Okay, now we're opening out again. So we've got the fast gas coming out. Now the area opens out, so it slows down. It doesn't need to go as fast now. It's got a bigger space to go through. So in this case, the velocity decreases, which means pressure and temperature can now increase. We can do the opposite of the velocity. So the main thing is to remember, whatever velocity does, pressure and temperature both do the opposite thing. A divergent duct, where can react to an engine aircraft, an aircraft engine, we can look here at a compressor. Okay. Where else might you see a divergent duct? What shape, let's give an example, what shape does, if we go to NASA, let's go to America. We've got NASA, we've got big rockets. What shape it exhausts on the bottom of the rockets? Convergent or divergent? The ones you see, the external ones, not the ones inside, because there's a bit of both going on. But what's the ones outside where the big fumes come out of? Are they convergent or divergent?
Convergent.
I think divergent.
Yeah, the last part is divergent. You are right. There is a convergent first and then bit divergent. They call them a condy nozzle, convergent, divergent. But the last part you see, if I was to turn this diagram 90 degrees and put this part on the bottom, I've got myself a rocket. Why is it divergent? Because they don't need, yes, the gas is coming out quite fast, don't get me wrong, but they need the pressure to lift that rocket off. Okay, they don't need the velocity, they need the pressure, the power to lift that massive weight up into the sky. And then once it gets momentum, you've certainly got velocity coming as well, but they need the pressure. Now, a jet engine, it doesn't need the pressure, it needs the velocity. It needs the speed of the gas coming out to propel the aircraft forward. Okay, but we're going to mix these together now to give a basic engine. So just remember that convergent, velocity increases, pressure and temperature decrease. Divergent, velocity decreases, pressure and temperature increase. All right. So as long as you remember whatever velocity is doing, the pressure and temperature do the opposite. Okay. Hence I've represented it by the red and the green here. So let's add them together. So what I've done, I've put the convergent nozzle on this side, and I've joined the divergent nozzle together. What have we got now? We've got Bernoulli's theorem tube, what we had earlier on. Yeah. So we've got high speed gas here with a low pressure and temperature in here. Then as it opens out again, we've got low speed gas but a higher pressure and temperature this side. We've just joined them together. Now a jet engine works the opposite way. So I'm going to change it about. So I've swapped the ends over. I've now got a divergent duct this side and a convergent duct this side. I've now made myself a very, very basic jet engine. Okay, a very basic one. Let's look at the front. I've made myself a divergent nozzle. Okay, I've swapped it from the back, I've put it on the front. The reason I made it divergent this side because we want air to come in. Yeah, that's good. And we want to compress it, we want to increase pressure. Yeah, we want to increase pressure, then we add fuel, which would happen in this area here. We'll add some ignition, go bang, and then it'll go out the exhaust. So the exhaust, the convergent duct here represents the exhaust, where we want the gas to come out as fast as possible. We've done the job in the middle, where we've gone bang, put it on fire, and all that sort of good stuff. So we want slow moving air at the front, but we want to increase pressure, and as you increase pressure, we increase temperature, which also helps making combustion happen. Once it's done all the good stuff in here, then we're happy, we want the gas going as fast as it can, and that will propel this engine forward, okay, because it's got the fast moving gas at the back. So this part here, certainly this part here, would represent a jet pipe on an engine. Okay, don't have this in the books, guys. I've just moved this about just to show you representation. Okay, so we've pretty much made a very, very basic shape of a gas turbine engine. Okay, is everybody okay with that so far? Does that make sense, or have you completely lost it? I know it's Monday. Everybody good, yeah?
All good.
Good man, good man. Okay, so now, as I said, swapped over a divergent convergent, instead of convergent divergent, a very basic jet engine. So the background history, we'll just recap that bit and then, as mentioned, the four-stroke cycle, a bit more in depth. So intake, compression, combustion, exhaust. As I said before, intermittent power, because we're only getting the bang or the power stroke on the third stroke of a 4-stroke cycle. But the principle is still the same. I said already, air comes in, we compress it, we set fire to it, and then expel it out of exhaust as fast as possible. Okay, so we can almost put a line up here for intake, compression, combustion. Yes, got combustion, and then we've got exhaust. So it's very, very similar. All right, and we'll explain what happens in here all the way. Now you can almost see, if you look at this exhaust nozzle here, what shape is this part and that part making? Is that convergent or divergent? Just this last little bit here. Yeah, so there we go. We're getting the convergent. Okay, don't worry about the shape of the drum at the moment here. This is a specific type of engine. But generally, though, we are, if you look from the width here to the width there, we've got divergent. I say don't worry about everything between the moment. We'll discuss this as we go along. But basically, this part here is pretty much sort of divergent initially. Once we get an intake on here, it is sort of divergent. It does look convergent at the moment, but that's the type of engine we're looking at. It takes a bit of difference. But what we want to look at here is convergent at the background, which gives us propelling expansion of gas. So we've got slow moving gas cold, we compress it, we put it into the combustion section, set fire to it, and then it comes out far quicker than it did when it came in. But the main thing to remember, going back to Bernoulli steam, is the mass of air is still the same. It's not changed. All the air that's coming here is going out the back end in this engine. Yeah. So the mass is still the same, but the volume has changed. Yeah. We've just put some fuel and heat into it. But what goes in must come out. And what we want, the result for a jet engine, is a fast moving air. Okay. Okay, guys, let's go for a quick break now. It's 10:15, so I'm looking for a break about this time. Come back in about 20 minutes, and then we shall move on to the next bit. Okay, let's see. Showing the right page. Yeah. Okay, so see you in about 15-20 minutes, guys. Okay.
Okay.
All right.
Acceleration out the back end. Okay, and the old piston engines here, all right, we're constant volume process, where the jet engines are constant pressure process. All mass of air, we compress it, heat it up, expel it at the back end quite quickly. So the overall effect is a high velocity of air compared to a small amount of velocity for the large amount of work at the front on a propeller aircraft. So overall effect is not expensive by graphics. Jet engine goes faster than a propeller engine. Okay. So jet propulsion, where did it all start? All right. So many years ago, back in the Greeks and that sort of thing, would let's just get this up in a minute. Basically, Greek engineers, Hero was the very first one to come up with a propulsion type system. Now, if I just get this to work, you might get this to work. Depends if the internet's working properly or not. Let's see. Not doing that one. Try again. That's working on there. No, that's not working. I'll try again. One last go. Might work, it might not. Oh, that should start spinning. I'll try and get to work one more time. Come on. Let's see. There we go. Right. So basically, what Hero invented was basically a round ball with two vents on the other side, filled with some water, with some heat underneath it. Now the vents are opposite directions, so one's going one way, another's going another way. So very simple, basic jet propulsion. We heat the water up, it's going to boil, it's going to let off steam, and hopefully what will happen is, because the jets are facing the opposite directions, they're going to spin opposite ways, which equal and opposite reaction, Newton's third law, will make it spin round and round and round. The very, very basic principle. And this was done by a Greek engineer, Hero, and that was done back in 120 BC. So that's as far as he got, unfortunately. He never made any aircraft, otherwise we'd be all fancy stuff by now. But again, way back in those days, they were even thinking about propulsion back in those days. Amazing. Branca was another one, using the same sort of principle. Again, a big sort of disc filled water, and you can see a narrowing section. So again, thinking about convergence, steam blowing out onto a basic paddle, and that propels the paddle around. And again, that was back in 1629 with an Italian, Giovanni Branca. Okay, so again, using gas steam coming out. So we're already thinking about steam propulsion, even back in those days. Quite amazing. Newton, even Google says it, Newton. Again, use the principle of steam, boiling water, fire underneath, and again, small exit at the back end, and actually providing the thrust. And depending on the size of wheels, providing again. So he was coming up with ideas of using jet propulsion. Instead of using horses, hence we've got a horseless carriage, but very, very underpowered, not much oomph at all. The size of these things and the weight, it didn't go very fast. But again, back in those days, it must have been amazing. And then you get onto the steam engines as well, again, through the years. So we eventually got up to early 20th century, up 1913. French engineer René Lorin, he came up with a very, very basic principle of actually, well, I'll tell you what, let's put some air in here. Let's add some fuel. Let's ignite it and see what happens. And he came up with a very basic known as Nathoid thermodynamic duct, which is basically the principle of a ramjet. Now, in these type of engines, there's no moving parts. There's no spinning propellers. There's no spinning turbines. There's no compressors. It's purely the shape of the shell. We'll have some methods of putting fuel into it, inducing air in, and once that air is going fast enough, and once the fuel mixed with the air, then we set ignition to it, then purely it will self-burn because you've got the fast-moving air going out this end, which will draw more slower-moving air into the front again. And it'll just keep going round and round and round. Not very stable, but certainly it's a very basic principle of one of the first early proper jet engines. And used to use the ramjets for training and experiments and such like. Certainly in the Second World War as well, some of the old V1s type things. So that's called a Lawrence engine, the very first prototype of the modern ramjet. So gas turbine engines themselves were first developed back in around about the mid-1930s, and the one that we use in the UK, or the godfather of the engines we call him, Mr. Sir Frank Whittle, passed a few years ago now. He was one of the first guys to come up with an actual jet in Britain. He wasn't the first though. It was actually a German from Bas van Ohain. He actually invented the first flying jet engine. The Germans beat us to it. And the first one was a Heinkel 178 flown in 1939. And that's what it looked like. First jet-powered aircraft. So the Germans beat us there. But Sir Frank Whittle, he came up with another version called the Gloucester Whittle. Came out to be outdone. And he actually invented the jet engine by mistake. He was trying to do something else, came up by mistake and went, oh, I could use that in an aircraft. So let's put it in an aircraft. And then the rest, as I say, is history. The first flight of this one was on the 15th of May, 1941. And it's a good day, remember, because that's the day I joined the Air Force. Not in 1941, I'm not that old, but I joined in 1990 on the 15th of May. So it was quite appropriate the day I joined up. So why do we use jet power? Why not just use propellers all the time, piston engines? Big advantage during the war? Well, towards the end of the war possibly. Piston engines, the power is intermittent like we saw already. So we're only getting one power stroke for every 1 in 4 strokes of piston engine, where a jet engine is constant. It's a constant burn. We can add more fuel to give us more power or decrease appropriately. So a bit more efficient. Driving propeller, well, creates extra drag. The fact that that propeller becomes a big disc and such, as it's flying through the air, that disc is acting as drag. Although it's providing thrust, it's also causing drag as well. The bigger the propeller, the more drag. Yes, more power, but more drag at the same time. Larger frontal area. The need to go higher, go faster and go greater altitudes. Well, propeller piston aircraft back in the early days, they can only go so high. Why do you think that might be? What could be a disadvantage of piston engines up at height? Anybody? What do you think could be a disadvantage of a piston engine up at height? What's there not as much of up at height?
Low dense and the propeller.
Yeah, there's less density. But what is there also less of? What do we breathe? Hopefully.
Oxygen.
Oxygen, yeah, there's less oxygen. Piston engines need a lot of oxygen. Jet engines, yes, we still need oxygen, but the way it's done is it needs a lot less. It's far more efficient and less oxygen at high levels. You get more thrust. But a piston engine will get to a certain height and go, that's it, I can't breathe anymore. It's not enough. And a propeller needs to be able to grab that air to push it behind itself. Well, if there's less air, there's less to grab onto. And if there's less to grab onto, a propeller just can't cope at certain heights. So the jet engine wins in that case. Gas turbines provide constant power because of less moving parts. Less moving parts make it lighter as well, although some of the jet engines are quite big. Efficiency uses cheaper and less volatile fuel. What do you mean less dangerous fuel? Piston engines, if you think of cars and motorbikes against lorries, big commercial vehicles, diesel engines, petrol engines. Well, diesel is not as dangerous as petrol. If you get a bucket of petrol, you put a match or lighter into it, up it goes. Yeah. If you were to get a bucket of diesel and put a match in it, it'll just go, won't do anything. Okay, the diesel needs to be atomized, whereas petrol is very volatile. It doesn't take much to set it on fire. So piston engines need the sort of the high volatile fuel, where gas turbine engines use pretty much a heavy paraffin. It's almost like a refined diesel to be effect. Okay, cheaper, less dangerous. You also get a better power to weight ratio. The fact that there's less moving parts in jet engine means you can make it slightly bigger, get more power, because piston engines have got lots of things. They've got big heavy cylinders, got heavy crankcases, you've got the pistons, you've got the connecting rods, you've got the bearings, you've got the crankshaft, you've got coolers, and on and on and on. So lots of weight. Yes, you make the pistons very big and very powerful, but at the same time, they're big and powerful, but also very, very heavy. In other words, we can have more reliability with a jet engine. So I'll take on the first sort of graph we've got. It's called a PV graph. Okay, I'll just make sure the right page here. And this is what we call a pressure volume graph, or a PV. Now it's got a Brayton cycle. The jet engine works on the constant pressure cycle, also known as the Brayton cycle. Okay, also known as the Brayton cycle. Piston engine is called the Otto cycle. Easy to remember. Think of Otto as an automobile piston engine. It's called OTTO. But for a jet engine, we call it the Brayton cycle, or the dual cycle. So on the graph here, we've got pressure up the left-hand side here. So from low pressure to high pressure, and we've got less volume to increasing volume on the bottom here. So what we're going through is the basic reduction of air, what happens to it through a gas turbine engine, represented by what's called a PV diagram, a pressure volume diagram. Okay, so we're starting at point A here. Now A, that represents the atmospheric point in the atmosphere. So what we're sat in now, what we're breathing, that would be the front of the engine before the air goes into the engine. So as the air goes into the engine, goes into the compressor, well, we start squeezing that air. We start drawing the air in, we squeeze it in. So if we're squeezing air, we're reducing the volume. So we're going back the way, we're going down the volume scale. So you can see here, this point A to B, the volume of air is decreasing, but as we're squeezing it, we're also increasing pressure. So the pressure goes up. Yeah. So we're decreasing volume, we're squeezing that mass of air, but we're increasing pressure. We've now compressed the air. So the air is now getting past the combustion section. We'll add fuel, we'll add ignition, and it will go bang. Now, although we say it's a constant pressure process, you can just see here, it's not to scale, obviously. It sees a slight drop in pressure. The reason being is when we set fire to it and it escapes out, we do lose a little bit of pressure, but we class that as negligible. So if we add heat and ignition, it's going to expand. So we've got the pressure here, we've added fuel, set fire to it, so that fire has to go somewhere, so it expands. So the volume increases again. So you can see here the volume scale there. So the volume increases, but we don't need pressure anymore, we just need velocity. So the volume will expand, and as it goes out, the exhaust, it increases the volume until it diminishes, and then we start all over again. So more air in, and squeeze it, set fire to it, and out the exhaust it goes. Okay, that's what we call a pressure volume diagram, or a PV diagram for short. Commonly known for your gas turbine engine, which is your Brayton cycle, also known as dual cycle. Okay. Everybody happy with that PV diagram?
Yes.
Yeah, all good? Good.
Yeah.
Okay. So now we're going to move on to gas turbine fundamental and major components. We're going to start breaking the engine down into various bits and pieces. Okay. And actually see what's actually happening. Okay, let's see. Right, so what basic components make up a gas turbine engine? Clues in the question. Well, we're going to have an intake. We need somewhere where the air comes in. Now, an intake isn't classed as a major component. Usually the intake, what we refer to an intake, is the part of the aircraft. But just for sake, we'll just say the intake is part of it. Multiple design types. We do have a very small intake, basically at the front of the engine. But the actual intake, where the air comes in first before the engine, that's usually classed as part of the fuselage. And we'll look at different designs as we look on. Then we've got a compressor, which as the air comes in, the compressor does what it says. It compresses the air and then hands it over to the combustion section. I'm going to look at two different types of compressors, two main types. Then, as I say, we're going to the combustion section, where the fire is, where they add the fuel and ignition. And we're going to look at four main types of combustion chambers. Then once we've set fire to the gas-air mixture, that air expands very quickly and then goes through the turbines. And the turbine looks like a compressor, but it's the hot side. The compressor is the cold side, the turbine's the hot side, and that's where the gas spins a turbine, which then spins compressor. We'll show you how that works later on. But for the moment, we'll just speak about the basic components. Finally, once the turbine's done its job, the gas has to go somewhere, so the exhaust directs the gas out the back of the engine, and due to the shape of the exhaust, that will propel the engine forward. And provided that's still attached to the aircraft, that will provide your movement for the aircraft. So that's your main components: intake, compressor, combustion chamber, and turbine, and finally exhaust for the gas. So let's look at it. Oops. We've got intake at the front there. Again, we look at a couple of different types. There's your compressor. So the air comes in, squeezes it down, and then sets it off to your combustion chamber, goes on fire, expands out, goes through the turbine, and then finally there's your exhaust. Okay, I'm going to look at various types of engine. Okay, so the very basic setup at the moment. So intake, compressor, combustion chamber, turbines, and exhaust. So we're going to classify those engines. Okay, let's just see. Them as a single spool, twin spool, a triple spool, and either a low bypass or a high bypass. There's also another one there called a pure jet, where which means there's no bypass of air, and that's what we'll speak about bypasses shortly. But you want to know the difference between single, twin, triple, high, and low bypass as well. What is a spool? I mentioned three spools there. So a spool is a compressor, a joining shaft, and then a turbine on the back. We call that a spool. Okay, so a compressor, a shaft, and a turbine. Okay, so a single spool is, as we got in the picture there. A twin spool will have two of these. A triple spool will have three of these. Okay, that's the difference. But a basic spool is compressor, shaft, and a turbine. Let's look. There's a single spool. You can see there, compressor. There's your shaft, and there's your turbine. Right. Twin spool, and this is a mixture. We've got a twin spool, what's called a twin spool low bypass. Now, go back to the single spool. This is what we call a pure jet, no bypass. And what I mean by no bypass is all the air that comes in the front goes out the back. There's no bypass of air. Okay, so a single spool, we call it pure jet. Pure air in, all air out. Okay. A twin spool low bypass. Well, we've got two spools, a spool within a spool. Now, the small spool, which is the green one here, that's your high pressure spool. Okay, high pressure. The one to the yellow is your low pressure spool, or LP spool for short. So HP and LP. The lowest one is always on the most outer side extreme, so the very front and the very back. Okay. So low pressure compressor, high pressure compressor, high pressure turbine, and the yellow, the low pressure turbine. Okay, so these are free to move within each other. The bypass refers to yes, we've got air coming in, but this time all the air doesn't go through the core engine where the heart of the engine is. Some of the air, you can just see here, there's a gap there and a gap there. Some of the air goes around outside the core engine. If we didn't have a gap there, this would just be a pure engine like we saw in the previous diagram. But we're actually bypassing some air. We're literally, some air is bypassing all the internal components of the main engine, okay? And then it joins up again with the exhaust. Now, the bypass here can be used for lots of things. We'll look at that later on. At the moment, there you go, a twin spool, low bypass. A small amount of air, both sides, or all around it should be, is bypassing what is classed as the core engine. So a twin spool is two spools, a high pressure spool and a low pressure spool, okay? A spool, well, as it sounds, we've got three spools, a spool, and a spool, and a spool. Now this is a high bypass. Now, if you look at the high pressure spool first, high pressure compressor, and there's a high pressure turbine connected to itself, yeah? Then we go to what's called the in-between one, or the intermediate interstage spool, an IP compressor, and that's attached to the IP turbine, okay? And then the final one, again, which is the most outside, is your LP, just like we saw before. LP compressor, or LP fan, and LP turbine. Now these three spools are all free to rotate within each other. The reason I have three more spools is, this tends to be a sort of European version where Americans tend to have two spools, but we class as a high bypass because look at the air coming in the front. There's a big gap now between, this is the core engine, yeah, in the middle. There's a big gap there, so most of the air is actually bypassing the core engine. And you'll find that most commercial aircraft in modern days, the big fan at the front of your engine, it's the cold air here that's getting blown out. That's the one that actually provides the thrust. It's not the air going through the exhaust. Yes, you do get a little bit, you might even be 25% thrust, but sometimes you're actually getting about 75, maybe 80% thrust purely from the big fan at the front. Now the big fan is really a propeller inside the case. Okay, when you look at the big engines on the front, you see the big fan at the front, and all it is covered in a case. So it's really like a propeller. Far more efficient than propellers. But the engine part here, that's just basically work as an engine, the propelling force. Okay, so three spools. You'll see some annotations. We've got N1, N2, and N3. We'll speak about annotation shortly. N in this case is for the spool, as in speed. N represents speed. 1 is number 1 spool, 2 number 2 spool, and 3 number 3 spool. So in this case, 1 would be low pressure, 2 would be intermediate pressure, and 3 would be high pressure. If we go back one stage, if we go back to a twin spool, if I was to put an N1 on here, that would be the low pressure spool, and I put N2 on this one, because there's only 2 spools, there's no intermediate one, then that would just be the HP one, because this is a twin spool. So that's your 3 basic spools. High bypass, lots of air getting bypassed around the core engine, providing the thrust. Go back one, low bypass, just a small amount of air, bypassing, again, your core engine. So it's just the terminology we're looking for at the moment. Okay. Now remember, spools, compressor, shaft, and a turbine. Well, especially in the case of the twin and the high bypass triple spools, it's a small spool here, the HP, the high pressure turbine, the high pressure compressor spool. That's the one that starts your engine. Okay, there'll be a gearbox underneath here, which will attach to some form of starter motor. Okay, we'll speak about those in the future books. That will spin this turbine and compressor together. Okay, once the engine starts, the gas will go through the turbine, which will then spin the IP turbine, which is connected to the compressor. So that starts drawing more air in. Once the gas goes through the IP turbine, it goes through the LP turbine. Well, the LP turbine is connected to your big fan at the front. So once that starts spinning, this will start spinning, draw more air in, and it'll repeat the cycle continuously, all controlled by certain control systems, obviously. Otherwise, it would just run away and blow up. So by just spinning one little spool first, it's far more efficient startup. If you go back to the single spool, you've got a big compressor, big turbine, so it's going to need a big motor to turn this big lump of a compressor first to get the air going in. So a triple spool is most efficient out of the 3 spools. Okay. So again, we're going to the bypass and just a breakdown of it. So again, just to make sure, pressure, high pressure, oh, let's check the spelling there. Low pressure, high pressure spool, bypass of air, and the bypass air. Now, I said that bypass air we can use for cooling, you can use it for pressurization and a few other bits and pieces, quite a lot there. But again, that's just a low bypass engine. Okay. Weight reduction between a pure jet where there's no bypass, you can be as much as 20% already just by having a twin spool instead of one big huge spool. So you can actually save some weight already.
Excuse me, sir.
Okay.
One wants to join the class.
What, sir?
One attendees want to join the class.
Somebody wants to join the class?
Yeah, someone.
Nothing on here at the moment.
Saurabh.
I've got 16. There's nobody saying they want to join on my thing.
Is there any request there?
There's no one in the lobby.
No, there's nobody in the lobby. No.
Yeah.
Okay.
Ask him to try again if he wants. But there's no.
Yeah.
I get a notification if it comes up, but there's nothing at the moment.
Yeah.
Ask him to try again. Yeah, nothing lobby at the moment. Oops. Okay, right. So that was the basic spools. So your single, it's a pure jet, twin spool, low bypass. Again, that tends to be more military aircraft. Your normal commercial aircraft are a triple spool, usually a triple spool. Some old American commercial aircraft are just a twin spool. Tends to be European, it'd be the triple spool. So we're going to look on to what's called a basic turboprop. Okay. Let's make sure there's any need to highlight there. That's okay. So turboprop engine. There we go. There's somebody just arrived now. I guessed. So basic turboprop engine. Forget the propeller at the moment. We've got a gas turbine engine. It's just a gas turbine engine with the propeller stuck on the end of the shaft coming out of the front of the intake. That's basically what a turboprop is. A basic gas turbine engine with a propeller on the end of it. There's 2 classifications though. Okay. Now the power to weight ratio of the average turboprop is 3 times better than the same type of piston engine with a propeller on it. Gas turbine engine a lot lighter, less moving parts, so get more power and certainly more efficient compared to a piston engine. Reduced frontal area. We don't have such a big, certainly the big old piston engines used to be called radial engines, like cylinders coming off everywhere, big huge things. Efficiency, far more superior. And a good one to note here in your books, guys, on a turboprop, the turbine tends to have more stages. What I mean by more stages is, if you look at this diagram here, they've got 1, 2, 3, 4, 5, 6, 7. We've got 8 sets of rotor blades. We'll speak a bit more in depth later on. But for the moment, in a compressor, that's got 8 sets of rotors. That's a stage. On the turbine, I've got 1, 2, 3 in this diagram. It's got 3 stages. Now you tend to find, and it's good to highlight or make a note in your books, that a turboprop engine will have more turbine stages or more rows of rotors compared to a basic jet engine. Okay, good one to make a note of. So a turboprop engine will have more stages, more rows of blades compared to a basic turbine engine. Now the reason for that is to drive this big propeller, if you just have one stage, like one row of blades there, yes, the gas will go through and it will spin it. But then as the gas goes through, it's sort of wasted because it's the propeller that's providing the drive force. So as the gas goes through the first stage to the second stage here, well, this turbine will grab some of the energy from the gas, and that will help drive the shaft. And then as it goes through to the next stage here, again, this turbine is going to grab some of the energy and help. So these extra 2 stages are helping to spin the shaft, which helps spin the propeller. Where on a basic jet engine, if we don't have a propeller, you just let spin the compressor. so we don't need as many stages. So a good question you might get an exam is, which type of engine would have more stages? It would be a turboprop engine. Okay, so make a note of that one. So exhaust thrust from a turboprop is roughly about 10% of the power from the engine. So all the hot gas coming out here, you're only getting about 10% thrust from the actual engine. All the engine's doing is propelling the propeller here, which provides 80, maybe 90% thrust. That's where you actually get the power. Okay. The jet engine part of the turboprop is only providing maybe 10% thrust, so it's not quite a lot. But certainly, it's spinning this propeller up to suitable speeds. Now we've got a twin spool here, and this is class what's called a fixed turbine. Now a fixed turbine means, again, twin spool, so we've got an H, this colour here is red, so that'll be your high pressure spool, so your compressor and turbine. Then you've got in yellow is your LP spool, so your LP compressor is your shaft, and your turbine. Now you can see here, the shaft goes all the way through to the front, and on here you would attach a propeller blade. We call that a fixed turbine because the propeller is fixed to the shaft on the compressor. Okay, we class that fixed. In other words, when this is connected to the engine, it is classed as mechanically coupled. The propeller is mechanically coupled. In other words, connected to the engine, so it will be affected by that. A twin spool with a free turbine, well, in this case, turbo shaft, you've got your compressor. Don't worry about that at the moment. But this time, the turbine here, okay, is connected to the blade at the front, but it's not mechanically coupled. The only thing that's spinning that is the gas coming out the exhaust, out the turbine of the spool here is spinning it. Where on here, it's actually mechanically coupled through the compressor. In this case, the propeller at the end here is connected to a shaft. Yes, there's no compressor. It's only got a spool, a turbine spool. That's all there is. So it's a free turbine. If you go to a jet, it's got a free turbine. You could spin the propeller, and you're not going to turn the engine. If you go to a fixed turbine and you spin the propeller, you'll start spinning the engine itself. Okay, so fixed and free turbine. Fixed turbine is mechanically coupled. A free turbine is only gas coupled. There's no mechanical driving components. It's only the gas from the exhaust propelling that turbine blade. Okay, 2 ones to remember there. Jet gas flows. This is just a representation of what's happened to the gases going through it. And again, the figures are just examples. Don't take note of these ones. So at the front of the engine here, we've got pressure, 14.7, 14.69, your standard atmospheric pressure before it goes into the compressor. As it goes in, even before it's going to combustion chamber, it's gone up in pressure already, 39 or thereabouts, and some various other different ones. And then eventually, by the time it's been compressed, going to combustion chamber, it's going to be maybe 440 psi potentially. Pressure stays roughly constant. You can just see at the end of the combustion chamber here, it's dropped a little bit. So it's pretty much constant. But once it comes out and it's gone through the turbine, the pressure's dropped to almost, we're back at atmospheric conditions again. Okay. Temperature, 15 degrees. Again, these two figures, your pressure at 14.7 and 15 is standard outside pressure and temperatures. As you squeeze it, the pressure goes up. Forget this one at the moment, that's just a basic drop before it hits the compressor. But you can see the temperature, because pressure's gone up, well, temperature's gone up, yeah? So we've slowed it down. It must be a divergent type shape because the rotors provide a divergent shape because of pressure rise. So pressure's gone up, temperature must go up. So 557 degrees Celsius, that's very hot. Think of your ovens. You're having a pizza in your oven, what, maybe 200 degrees? Well, already before the air has gone to the combustion chamber, it's almost at 550 degrees. That's very hot already. Then eventually goes in the combustion chamber. These figures are just basic figures. It's got pressures roughly the same, temperatures doubled. Some of the cases, the temps can reach almost 2,000 degrees. Okay, 1,800, 2,000 degrees. Then as the gas leaves to go to the turbines, it'll start to cool down, pressure will reduce. It's still quite hot, 771 there. But to be honest, sometimes the turbine's about 1,500 degrees. And then when it gets to the jet pipe temperature, we're maybe down about the 500 degrees point, and the pressure's back to pretty much normal. But the speed of the gas coming to the back is a lot faster than it was going in the front. Okay, so it's just a basic insight of the gas flows. What happens to the gas flows? It goes through a basic turbine, a basic engine. Well, here's the front of the aircraft. Okay, so intake of engine here, going through the compressor. All right, as it goes through the compressor, now the compressor blades are divergent in shape because as it's spinning through, it goes through what's called a rotor and a stator. Now the rotor is a bit spinning, it's called the rotor, and the stator is a bit, it doesn't move, it stays in the casing. So as the rotor spins, it pushes the air backwards. So there's a rotor, the stator, and that will guide, the stator will guide the air onto the next rotor, and so on and so on and so on and so on. So, and we call that stage. A rotor and a stator is classed as a stage. Now, in between each stage, they are divergent in shape, so pressure will rise between each stage. And that's represented here by the pressure going up in the graph. Okay. Now, on this type of engine, we'll jump ahead a little bit. This is what's called an axial flow compressor. If we just increase the pressure per stage, what's going to happen to velocity if we don't do anything? Pressure and temperature go up, that's fine. But what will happen to the speed if we just keep pressure, 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 pressure? What will happen to the gas speed here, to the gas speed there, if we don't do something? What do you think? Anybody? If we're increasing the pressure per stage, so we increase the pressure here, we increase the pressure here, 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 and so on and so on, depending how big the engine is. What's going to happen to the speed of the air? Is it going to increase or decrease?
Increase, increase.
If we don't do anything,
Yes, velocity increase.
It's going to decrease. Forget the graph at the moment here, but if we don't do anything here, it will initially start decreasing. Now, on this type of compressor at the moment, just jumping ahead a little bit, we want to increase the air, yes, but we don't want to lose the speed of the air. All right, we want the speed of air to stay pretty much constant as it goes through there. If we remember, if we go back to convergent dot, divergent dot, if velocity increases, pressure and temperature decrease. Well, in a compressor, the pressure is increasing and so is the temperature. But if that's doing it at every stage, then eventually the speed will get less and less and less. Now, in this type of engine, which we call an axial flow one, by the shape of where the blade's attached to on the compressor drum, we make, and you see from here to here, we make a convergent shape. Yeah, so the speed of the gas is going to speed up. So as it slows down, it speeds up, it slows down, it speeds up. So maintaining the flow of the air through there, we use a convergent shape between the casing and the drum with the compressor blades attached. We'll speak a bit more in depth later. Hence why the actual velocity here is pretty much constant. Okay, yeah, it goes up a little bit. So in the compressor section, we've increased it, squashed the air. We've now gone to the combustion section. Now, just before the combustion section, this part here is called a diffuser. Okay, just give some names at the moment. You can see here that is slightly divergent. We don't want that fast-moving air, which is compressed, hitting combustion chamber too quick, because that could blow the flame out. So we do a little bit of divergent, which slows it down a little bit. And if it's divergent, well, pressure's going up again. So we slow it so it's controllable speed, a little bit of pressure increase, then we put it into the combustion chamber, we add some fuel, and it goes bang. Yeah. So the pressure here, almost the same. It does drop a little bit because we've got an open point here to the nozzle, so it's bound to drop a little bit. But the volume is going to increase rapidly because we've expanded it by adding fuel and ignition. So that hot gas is now coming out really fast from the combustion chamber. Look at the combustion chamber. What shape is it making here? Convergent or divergent?
Convergent.
Convergent.
Yeah, we don't need to compress it anymore. We've done the compression part. We just want that gas to come as quick as possible. So we're now converging the gas. We'll hit what's called an NGV, nozzle guide vane. Okay, that will then hit a rotor blade, which is a turbine rotor. That will spin the turbine. But remember, the turbine is attached to the shaft, that shafts have touched the compressor. So as the turbine starts to spin, it's going to spin the compressor faster, which will draw more air in, go and fire more, and so on and so on and so on. The cycle keeps going over. And it depends how many stages you've got. In this case, we've got 1, 2, 3 stages of turbines in it. And then as it leaves the turbine, it goes out to the exhaust nozzle. Okay, and again, the propelling nozzle, you can just see here, there's a little lip here, imagine down here, that convergent. It does look a little bit divergent initially. We'll cover that later on. But the very end point here is convergent. Okay, and that's represented by there. So go back to the front, increase pressure, good. Goes bang, or burn in this case. Pressure almost stays the same. The temperature obviously goes up. All right. As it goes to the turbine, don't need pressure anymore, but the velocity, if you look at the velocity now, which has slowed down, has now increased. And then as it goes to the exhaust, it goes really quick, yeah, through the propelling nozzle here. All right, so that's a representation of how the gas flows through. All right. Nice to see the representation up to about 3,000 degrees. If you look about there, yeah, we're about 1,000 degrees, but the flame tube, we're about 2,000 degrees. Very, very hot. Now, we briefly mentioned notations, just for a break there. N was speed, P is pressure, T is temperature. So if I said to you P0, P nothing, okay, well that's what we're in now, standard pressure, atmospheric pressure. So P0 would be just before the intake, atmospheric pressure. P1 is in intake, so it's intake pressure, and that can be affected by the forward speed of the aircraft. Now, when we go into control systems way down the next few books, the computer, if it's a computer organised control system, needs to know the pressure here against the pressure outside, which can then say, yes, I can have more fuel and stuff. But don't worry at the moment, just think about annotations. So in a basic single spool compressor engine, we've got P0, P1, and then P2, which would be compressor delivery pressure. Okay. P3 in this case would be turbine entry or combustion chamber outlet pressure. Then P4 would be turbine outlet pressure, P5 exhaust, and P6 nozzle in a single spool. That's sort of a very basic one. A twin spool, and this is where most of the questions come from. Most questions come from a twin spool type scenario because we've got 3 spools, so 2 is the average. So if we look at the front again, we've got P0, we've now got T0. T is temperature, so the temperature, atmospheric pressure. P1, intake temperature and intake pressure. P2 and T2, that would be the back of the LP compressor, because remember this is a twin spool, so LP compressor, LP turbine. HP compressor, HP turbine, okay? So, then we go back to P3 and T3. Well, P3 is HP compressor delivery. That's the air before it goes in the combustion chamber. And likewise, T3. Then we get to P4 is combustion chamber outlet and temperature outlet. P5, HP turbine outlet, same for the temperature. And P6 would be LP turbine outlet. Then P7 is your jet pipe, and P8 is your nozzle. Now, the easiest way to remember this, numbers are from left to right, 0 to 8. They might have 9s, they might have 10s, but generally that's a basic setup. Now, if you remember that anything up to 3 is the cold section. Although it does get quite hot here, looking at 5 degrees, think of all the numbers up to 3 for a twin spool as the cold section. 4 and above is the hot section. So 4 is combustion chamber outlet, okay? So if you come to exam, you can't remember which one's which, just think 0, 1, 2, 3 is cold on a twin spool and above. 4 and above, that's hot, okay? And it's worthwhile just drawing a very basic diagram out, basic engine, do a twin spool and such like. Now we mentioned the stages. Look at this compressor here, the LP compressor. I've got 1, 2, 3, 4 sets of spinning rotors that make up a compressor. So we class that as a 4-stage compressor. Let's look at the HP compressor. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 sets of rotors, yeah? Compressor blades. So that means that's a 12-stage compressor. There's a little dashed line here. Now, I usually put a little red line here. If I was to pick a point at the 1, 2, 3, 4, 5 point, fifth stage, I put an arrow there, that would be, for pressure temp, that would be P2.5. In other words, it'd be compressor delivery, the fifth stage, 2.5, so that's the fifth stage. So if you see an annotation with point something, that just means the stage. If I put a point here, that would be P1.2, because it's the 1, 2, the second stage, okay? Just in case you come across like that. Triple spool, again, the P0s, P1s, the T1s, the 2s, the 4s, the 5s, the 6s, 7s, and 8s. But this time, we've also got N1, N2, and N3. Your N1 is your LP spool, your low pressure. N2 is your IP, the intermediate spool. And N3 is your HP spool. Okay. Now, important thing to remember on any spool, if you look at the back of the jet pipe, you'll see the turbine. Yeah, you could actually go and spin the turbine. It is always the low pressure turbine. Okay, always the low pressure turbine or the low pressure spool. So for a single spool, where you're looking at me in the diagram, I'll probably back to front for you guys. If this hand here is a compressor, then your shaft and a turbine, well, the turbine is going to be the basic turbine. A twin spool, it'll be compressor, LP turbine, we come into HP compressor, HP turbine. So the outside one is always the low pressure. Okay. Triple spool, LP, next spool, IP, next spool, HP, which is the smallest one. Again, on the outside, if you look at the jet pipe, it is always the LP turbine you will see, or what's classed as the rearmost rotating component. All right. Front of engine, it'll be the fan. The back of the engine, it's always the LP turbine. If you get a question, good one to make a note of there. Okay. Again, we'll recap this a lot, don't worry. Right. Okay, any questions on annotations there? Everybody okay so far? Okay, move on to intakes. So we need to grab that air, push it into the front of the engine. So what's the purpose? It will introduce the air compressor. Without an intake, we will just be trying to grab air all over the place. It's no good. So we need to direct that air into the compressor. Minimum energy loss. We do get a bit of drag because obviously the intake's at the front, and we get a bit of pressure loss as well, but just negligible. It provides clean air, free from turbulence and debris as well. We need to direct that nice clean air, nothing else in there but pure air inlet, and direct it to the front of the compressor. It depends on the type of aircraft you're working on. There's no ideal place for intake. We have an engine where we're fitted, wherever the intake is, well, that's where the engine is. So depending on the aircraft, there's positives and negatives of each type of intake. If you look at this diagram here, we've got an engine which is in the middle of the fuselage at the back here, and it's got an intake on both sides. The air goes into one engine in this case. This looks like a wee Hawk aircraft. Now, going forward, that's fine. Air's coming in straight on the aircraft, and it's getting directed into the intake. You'll get a small loss of build-up boundary layer. You go back to modulate boundary layer air as it sort of turbulence goes towards the intake, but at the moment it's fine. But an aircraft never flies straight. It's turning, it's pitching, it's doing whatever it's doing. Okay, so as soon as the aircraft starts to turn, the relative airflow position changes. So if you look at this aircraft here, okay, it's turning. So yes, we'll get airflow coming in this direction now, but we're going to cause a bit of turbulence and separation on this side. So we're actually inducing some rough flowing air into the intake and mixing with the smooth air. Now that's okay. Most aircraft are designed, obviously, to take that to a point, provided the pilot flies that aircraft, if you remember going back to modulate days, within the set envelope, the parameters of the design of that aircraft. If he starts throwing it about like he's in Top Gun, and then he's going to get flat spins, God knows what else going on. Okay, so as long as they're flying within the parameters, the height, speed, etc., and what the aircraft is designed for, then it'll be fine. But you can see here that obviously some positions can cause a bit of a problem. Other examples. We've got intakes on the wing here, and we've also got one at the back on top of the spine, fuselage. Now, aircraft turning left and right, not too bad because the engines are on the outside, so it doesn't matter really if it turns a little bit. It will get a bit of deflection from there, but they're not as close to the fuselage as we saw in the previous one. But this poor engine in the back here, turning doesn't cause a problem. But what about pitching when the aircraft's taking off? As it goes forward, the fact that the aircraft's pitching up, it's going to block the intake off a bit. If it gets too much angle of attack, it can actually block some of the air off. So again, the aircraft has to be flown in the correct parameters that's required. So again, just showing you it doesn't really matter where the engines are. Yes, on this one here, you've got engines are on the wings, great. The ones outside, well, imagine aircraft's turning. Well, this engine here is going to turn faster than the inboard engine, isn't it? When the aircraft turns, closer to the fuselage, the slower that position's moving. Where the one further out, that's going to move faster as the wing's coming round. So that's going to induce more air into it than that one. So again, it all depends on the design of the aircraft. There's always positives and negatives. You'll never get an ideal position. Some aircraft and military aircraft have an intake underneath the front of the fuselage. If you pick a military F-16 aircraft, they've got a little, what's called a scoop type intake. Again, turning's fine. Angle of attack, if it goes on a dive, that blocks off the air. So again, there's positives and negatives for different designs. But these aircraft are all designed to fly a specific way, a specific manner, a specific envelope. Okay. So, look at the first type of intake, the basic one, the ones you guys are probably working on, we call what's called a subsonic intake. In other words, below the speed of sound. So the air coming in is below the speed of sound. And you can see it's nice round shape there. Okay, it's nice round shape, and that helps guide the air into the front of the fan here. Okay, compressor. Now, make a note of this one. It is a slight divergence of intake section towards the compressor or the fan. There is a tiny little bit of convergence at the front, but for the purpose of exams, as the intake, if you actually go into the intake, it opens out. Okay, so from the front, it's quite narrow, and it opens out towards the back. So it makes a divergent shape inside the intake. That helps stabilize the airflow, it slows it down. But if it's slowing it down, it's going to pressure increase a little bit already. So even before the compressor's done anything, the pressure has started to build up. Okay, so it's worthwhile making a note of that one there. Slight divergence, and it's what's called ram effect. And we'll speak about ram effect later. Now, this type of round intake, or subsonic intake, is also known as a pitot type intake. You might have heard of pitot probes, which do the same sort of thing. But a round one is called a pitot intake. Subsonic, suitable for speeds from below speed of sound to what's almost transonic. It doesn't go supersonic. If it's going supersonic, the jet's in trouble. It's coming down like that very, very fast. And that's the last thing you want to worry about. Okay, so below the speed of sound. This looks like a 77 because you've got the round intake, but it's flat at the bottom. Okay, it's not, it means there's a flat bit in the engine, it's just the design because of clearance. On the 737s, there's not much of a clearance between the ground and the intake. So what they do, the front of the intake, they actually make it slightly flatter just for ground clearance. It's not been squashed down like that. Okay, so just a different version. Other types of intakes, integral to the wing. This is off the Comet aircraft, which is the predecessor of a Nimrod aircraft I used to work on. Again, the engines, we've got 4 engines in this aircraft. They're way back down here within the wing. Okay, so these are actually integral to the wing design. Again, these are subsonic intakes, doing the same job and just the type that they are. So, looking at the front of a basic pitot type intake, nice and round, forming divergent as it goes down towards the compressor. Okay, so airflow directly through the intake, all right, and onto the fan in this case. You can just see here, you can just see a slight slope up there and a slope down there. Well, there's your divergent shape before the compressor. You can just see a very small amount of convergence though. So initially it grabs the air and then opens out. Okay. Now, pitot intake is able to maximise the use of what's called ram pressure. What do you mean by ram pressure? Is the effect of the aircraft as it flies. See my hands intake. As the aircraft's flying through the air, the faster it goes, the faster air is getting rammed into the intake. And we use that as ram pressure. We'll speak about that in the fuel systems. So the air stationary aircraft grabs the air, the faster it's going, the faster it's ramming that air into the intake. And that will determine how much fuel we add to the engine. So it can make effect of that purely by design. So it's taken from the forward speed of the aircraft. So looking there, on a pitot type, again, you can see the divergent shape of the intake. Again, a small bit of convergent shape here. So at low speeds, yeah, it's pretty much taking all the air in, all quite happy. As the design Mach number, the speed of getting to course, the speed of sound, it's, yeah, it'll take that just. If it's going faster than the speed of sound, something's seriously wrong with the aircraft, it won't take the excess amount of air. It will only take the designed amount of air it's designed for. Okay, so normal, start of an engine up, and normal flying. Okay, so they are designed to use only that amount of air. So that was subsonic intakes. Any questions on those? Just make sure I'm not missing anything there. Examples in the book. Main thing to remember from those: subsonic is below speed of sound up to about transonic, so transitioning speeds, and they make use of a divergence shape from the tip to the compressor. Okay, and they make use of ram speed, ram effect by the forward speed of the aircraft. That's the three main sort of things to remember from those ones. And then we go into what's called supersonic intake. So I'll just mention this one, and I'll go for a quick break and come back because I just noticed the time there. So supersonic, as it sounds, going faster than the speed of sound. So we use various types of those. Now, you'll probably never go and work on a supersonic intake unless you work in the military or a specialist aircraft. Okay, so we do mention this because we did have the Concorde, remember the name. The reason we still speak about supersonic is because they were on about maybe bringing the supersonic aircraft back in. Now, there are companies designing hypersonic aircraft, never mind supersonic, but hypersonic aircraft. So you never know. Days down the line, you might get to work on one. So supersonic intake, this is where it makes use of con-die nozzles or divergent nozzles. Okay, now, when you go supersonic, you're going faster speed of sound. So the aircraft's going faster than airflow. And you probably heard the sonic boom. You ever heard the term sonic boom? So when you're flying through an aircraft through the air, you'll get this bang. That's what's going faster speed of sound. The air can't compress anymore, and it makes a shock wave. Now, if you have shock waves hitting an engine, the engine can't cope with that. So it's up to the intake to make sure that the airflow that hits the compressor is suitable and slow enough. So if you look here, we've actually got a bit of a convergent shape going on. So there's a shock wave at the front represented by these lines. It's a little bit of convergent. So it's convergent, it speeds the air up. Well, wait a minute, we're already going fast in speed of sound, but if we speed it up, the pressure and the temperature drops. So the pressure of the shock wave will drop to a manageable amount that when we get to a divergent shape here, it goes, okay, I'm slow enough, I can now breathe. Ready for the front of the engine. And that was the early types. Basically, we're controlling the shock wave. As it comes down to this point here, it's then manageable. We don't want shock waves hitting compressor fans. They'll just explode. Okay. So early ones use a convergent, divergent type nozzle. There's our Concorde at the back there. The Concorde's intake at the front, quite square sort of looking type intakes. Now, this part here, it's hard to see in the photograph. I think it's the same one in your book, if I remember right. Just double check. Yeah. If you look at the top inside the intake here, this part, or just behind it there, sorry, that part actually moves. It's called a wedge or a ramp. We call them ramps or wedges, and it actually moves up and down. And that does the job of this fixed convergent divergent nozzle. Okay. And that, depending on the speed of the aircraft, how fast it's going, will move down or up accordingly. So let's have a look at that one. So if you go back there, oops, there's the intake. We're just going to side on now to a side on view. There's that wedge or roof that comes down and up. Okay. At supersonic speeds, that roof, or the wedge as we call it, it's called a wedge, it comes down. So what it does, there's the fixed bottom of the intake, so it reduces the gap. So it makes a convergent shape. In other words, it reduces the pressure of the shock wave coming in, makes it manageable. Then it makes a divergent shape as it goes back towards the engine here. So if it's divergent, pressure will go up again, that's good, but it's also slowed down. It's also slowed down, okay? So the engine can now cope with that. If that was fuel up at supersonic speed, it'd just be a massive fast flow of air with a big shock wave and just bang and hit the engine, like hitting with a sledgehammer, which is no good. You'll also notice we've got a dump valve and a spill valve, okay? The dump valve will open to dump, as it says, any excess amount of air, same as a spill valve, okay, depending on the type of valve we've got. So that's at supersonic speed. So remember, the wedge comes down at supersonic speed. So at subsonic speed, for starting the engine up, or maybe slow speeds, the wedge, in this case, is now back up out of the way. So the gap has increased because the engine can cope with the slower speed and volume of air as well. Okay, so high speed, wedge down, low speed, wedge up. The dump valves are always open. In this example, dump valve's facing back away because we don't want to rip the door off. In this case, the dump valve is used to scoop air in because we need some extra air coming in. The spill valve will open accordingly to help prevent choking the compressor in turbulence. So between these two valves, they control how much excess air or not enough air is going in. So high speed, there'll be too much air, so it will open accordingly. At low speeds, it will scoop some air in to help make sure there's enough air for the compressor, whilst at the same time the spill valve will prevent turbulence and that sort of stuff. So we've got supersonic, wedge down, subsonic, wedge up. The dump valves will open both ways. Okay. Right, let's go for a quick bit just as the time is flying on there. Yeah, come back, what time's that? 22. Come back at 12 o'clock. Well, I said 12 o'clock. Come back in 20 minutes. And then before we go into ice protection, we'll do a bit of recap and then we'll go for lunch. Okay, so 10-minute recap after this break and then we'll go for lunch. Okay? Any questions so far? Everybody still awake?
Yeah, we are awake.
Ah, that's good, that's good. You've not fallen asleep yet. That's not so bad. Okay, so yeah, come back with 20 minutes and we'll do a bit of recap. And then after lunch, we'll do ice protection system. So come back in 20 minutes, 10-minute recap, 15-minute recap, and then 15 minutes before lunch. Just a bit of recap what we've done so far. So I'll just go back to the book, who we see fit, and we'll go around and see what we remember. All right. So just as we've got, if I've sent to you, make sure we've got volume. There we go. Okay. So we spoke about just for a break there, the supersonic intakes. Now I mentioned the wedge or the ramp. Now, what position would the wedge be in if the aircraft was going supersonic? Would it be down or up?
Supersonic, the wedge will be lower, down.
Lower.
Good. Yeah, always in the low position. So the wedge would be in the down position. Good. That reduces the size of the shock wave, lets it go faster so the engine can cope with it. Good. Okay. With a subsonic intake, where does it make use of ram effect, or how can a subsonic intake make use of ram effect, and where does ram effect come from?
The ram effect come from the forward speed of the air.
Yeah, that's good. Yeah, so the aircraft's coming forward with intake and it grabs the air as it goes. Now, the faster the aircraft's going, the faster ram effect. The more more air's getting rammed in. And we'll come to the fuel systems later on through the week. You'll see how that affects the amount of fuel that goes into the engine and such like. Good. Okay, what shape does the subsonic intake make from the tip towards the compressor?
Is it slightly divergent?
Yeah, slightly divergent from the tip. Yeah, you do see a very, very small piece of convergent right at the very tip, but forget that for the moment. The generally is divergent from the front to the back towards the compressor. But there is a small amount of convergence at the front, but generally divergent all the way through. Good. What is another name for a subsonic intake?
Low supersonic, very low supersonic.
It doesn't go supersonic. There's another name for it. It can be subsonic up to about transonic, but what's the overall name, another name we call it? Starts with P. Remember the name?
No.
What was the question?
It's the name of a subsonic intake, also known as a something type intake.
Pitot type.
Pitot type, yeah, good. Yeah, you'll see, in fact, on this diagram I've got at the moment, oh, maybe not very well, that's probably just about it. That might be one there, it's hard to tell in the diagram at the moment, but that could be a little pitot probe, you know, same sort of thing. Probes are called pitot probes as well. Again, we'll cover that later on. Yeah, a subsonic intake is also known as a pitot type intake. Good. And what's the purpose of an intake? What's its main purpose for an intake?
To introduce the air in the engine.
Yeah, nice, clean, debris-free air. Good. All right, we'll go back away. I'm just going back through the book as we've done already. We'll go into annotations. If I say to you, what is in a triple spool engine, what is N3?
HP spool.
N for November 3. What would N3 mean?
LP spool.
Not LP.
This is high pressure spool.
Yeah, high pressure, yeah. If I said to you in the same engine, what would N2 mean?
Low pressure.
No. Triple spool engine, or N2.
Intermediate pressure.
Yeah, intermediate or interstage. Just think of it in between. You've got your standard twin spools, LP and HP, and then one in the middle is your intermediate or interstage spool. Good. Okay, if I said to you in a twin spool engine, what is P3?
High pressure compressor.
Yeah, and a bit more. It's not just
High pressure compressed delivery.
Yeah, compressor delivery. Yeah, P3, P for pressure. So it is a high pressure compressor. Delivery air. Yeah, it's the back of the compressor, the air before it goes to the combustion chamber. Good. Okay. If I said to you, what is P4?
Combustor outlet.
Yeah, combustion outlet. Good on it. Twin spool. Good. If I said to you, what is P8 on same engine?
Is the nozzle of the engine.
Yeah, basically the propeller nozzle, convergent shape and propeller nozzle. Now, when it comes to controls, the engine fuel controls, air controls, whoever control system's in charge, whether it's mechanical, electrical, or computer, whatever, it needs all these sensors. So it can sense the pressure at the back of the engine, the pressure at the front of the engine, so it can determine how much fuel, if it's getting too hot, if it's got T references and that sort of thing. So they're all working together, providing input back towards the control system to determine that yes, it's okay if you have more fuel, or no, that's too much, not anymore, and that sort of thing. So that's why we need all those sensors there. Good. What was another name for a jet engine cycle?
Brayton cycle.
Braking cycle, yeah. It's also known as a dual cycle, but more commonly known as
constant cycle.
Yeah, constant pressure. What would it be? I've not got in the book at the moment, but do you remember what it called a piston engine cycle?
Because it's operated in 4-stroke cycle.
Yeah. So another name for a piston engine cycle? I think it's in the book now, but I did mention it. Constant volume, or known as the Otto cycle. Okay, doesn't come on that. It's not so much in the book now. Okay, what's the difference between a fixed turbine engine and a free turbine engine?
In free turbine is not connected with the spool
Good.
of the compressor.
Well,
yeah.
yes, it's not mechanically coupled. That's the main word. It's free to rotate. The only thing that it rotates it is the gas coming from the HP turbine. So there's no mechanical gearing. It's just purely a shaft with a turbine and the propeller attached to it. Now, saying that, there is a gearbox at the front for the reduction gears, but we'll come on to that later. But yeah, with a fixed turbine, it is fixed. It's fixed to the compressor and the gearbox and that sort of thing. Good. Okay. What's the difference between a low bypass engine and a pure jet?
In pure jet, we do not have bypass duct.
Yeah. So yeah, some of the air goes round. It's still within the engine itself, but not the core engine. Yeah. So the standard commercial aircraft you'll probably work on is probably a triple spool, maybe a high bypass engine. So you got basically the fan at the front, which provides pretty much all your thrust, and a large gap between the fan and the core engine itself. So that all the air is bypassing the core engine, and you can use that air for cooling. You can use that air for obviously thrust mainly, but it can also help reduce noise as well, which you'll see later on. That's confirmation from Sanjeev that he's got the new books, so hopefully he'll be printing those out for you soon. Okay, I was going to say page number, but you can't use the page numbers at the moment. Just give an idea. Having a low bypass is around 1:1. High bypass can go from 1:1 to 6.5. Some of the high bypass engines nowadays are a 10:1 ratio. So in other words, 10 parts air bypasses the actual core engine. Yes, yeah, so it's quite a large amount, and they're getting bigger and bigger each time. High bypass engines, although they're very quite large diameter, they're actually, if you look side on, they're quite short. Where a pure jet engine, longer, heavier, and that sort of thing. So by having the shorter engines, it's a bit more efficient as well.
With a lot of noise.
Yeah. Other things I want to mention, again, I can't put in your books because you've got different books at the moment. Just be aware that the bypass air is called the cold stream air. I forgot to mention that on the slides here, cold stream air. The non-bypass air, the air goes through the core engine, that's called the hot stream. Makes sense. It's the main part of the engine. So it's the hot stream air goes to the core, and the bypass air is called the cold stream. So when you come to looking at bypass ratios, it's the difference between the cold stream and the hot stream. That's what the ratio is. Okay. All right. Good. What was the construction of a spool? Yeah, and then if it's a twin spool, it's 2 of those, triple spool, 3 of those. And what I said before is if it's a triple spool engine, if you look at the back of the exhaust and you see a turbine, what turbine would that be in a triple spool?
Low turbine.
Low turbine, okay, good. If it's a twin spool, what turbine would it be?
It is, of course, low turbine, yeah?
Low turbine, yeah. If it's a single spool, what would it be?
Low.
If it's a ramjet, what would it be?
No.
Nothing.
Nothing.
There's nothing in a ramjet, yeah? I usually catch my students out of that back home. It's usually somebody says low turbine. There's nothing in a ramjet. Good. Good. Okay. All right. What does a PV diagram represent? A PV diagram.
Brayton cycle.
Pressure cycle.
It's pressure against volume. Yeah. The positions A, B, C, D. Pressure against volume. Okay. Right. So what I'll do, I'll just recap a little bit because your books aren't obviously quite exact the same, although book 1 new style and book 1 old style is quite close. We didn't change too much in it. If you look into your major components, the compressors, the combustion system, turbines, remember that a turbine extracts the gas flow from the combustion chamber. As it spins, the turbine spins, it's connected to a shaft. The shaft's connected to a compressor, so that's going to spin the compressor quicker, which will draw more air in, and so the whole cycle will continue, depending on the controllability of the system as well. Okay. The history of the stuff, you're probably not getting any questions on the history, so you might be okay with that. There might be one little one in, but again, it's more for a background introduction, so don't worry too much about the background or the history. Just be aware of how we basically came across to the introduction of turbines and engines and stuff like that. The only thing you might want to remember is the difference between a piston aircraft and a jet aircraft. Which one uses a large amount of air to produce a small velocity?
Turboprop.
Yeah.
Yeah, sort of piston aircraft one, where the jet engine uses a small amount of air, gets a large velocity. Yeah, that's probably the only one I want to remember. Relationship between 4-stroke and a jet engine is pretty much the same. Induction, compression, power and exhaust. For a jet engine, induction is the air coming in. Compression, well, compresses the air. Combustion or the power, yes, it goes bang, or in the case of a jet engine, it goes burn. And then blow would be the exhaust gas coming out the exhaust. Okay, so pretty much similar there. Possibly you might get questions on convergent divergent like you did in physics. So remember what happens in a convergent duct?
Velocity increase, other pressure and temperature decreases.
Yeah, that's it. Whatever velocity does, pressure and temperature do the complete opposite. Yeah. Okay, if I said to you, what's the name for the constant pressure cycle?
Yes.
Brayton cycle.
Brayton cycle.
Yeah, and so what would you be if you had that reference to the universal gas equation? What would you be left with as an equation? Out of the universal gas law equation.
P1 V1 by T1 equal to P2 V2 by T2.
Yeah, so in a constant pressure cycle, what would you be left with?
Volume and temperature.
Yeah, volume over temperature. Now, is that directly proportional or indirectly proportional?
Directly proportional.
Yeah, good, because if volume goes up, so does temperature. Yeah, if you heat something up, if you're in a room and the door's closed, you put your heating on, the air in your room heats up, well, it's going to expand. Well, it potentially could expand, so it gets so hot, it could blow a window open. We open the door, that hot air will escape. Basics of a jet engine, yeah? The temperature scales on that, don't worry too much. I mean, one thing you might want to remember is a thermodynamic engine is thermodynamic is never 100% efficient. Heat energy is expressed by the letter Q. W is work, so you get heat energy coming in. Whatever work is done by the engine is good, but we'll always get left with something we don't get. So it's Q minus W, excuse me, is rejected into what we call heat sink. Sometimes you get a question on that, sometimes you don't. Okay, what's the formula for power? Power equals what?
Mass at time acceleration.
Energy over time.
Energy over time, yeah, that's the main one. And what are the standard units for power? What are they measured in?
Joule per second.
Yeah, or I used to call it joules.
What?
Watts or joules? Yeah, energy over energy is joules. Good. Okay, that's it. Just a little recap there for what I've done so far. That's just taking us up to lunchtime. So we'll go for a way for an hour, come back to lunch, and then we'll start on what I've got there.